Hey guys, welcome to Pre-Calc, Lesson 7.6, Mathematical Induction Proofs. All right, let's take a look at what an induction proof is. First, I want you to use the pattern for the sum of the odd integers to develop a sum rule. So if we're talking about the odd integers, it's 1, 3, 5, 7, 9, so on and so forth. Let's take a look at some partial sums. For example, what is the sum of the first term? Well, that's pretty easy, that's just 1. How about the sum of the first two terms? That would be 1 plus 3 equals 4. Sum of the first three terms would be 1 plus 3 plus 5. That equals 9. Sum of the first four, 1 plus 3 plus 5 plus 7. That equals 16. So let's see if you can predict what the sum of the first 9 terms is. Did you get 81? You're correct. How about the sum of the first 15 terms? 225. So if you got those right away, you sort of picked up on this pattern. The sum of the first term is 1. Sum of the first 2 is 4. Sum of the first 3 is 9. Sum of the first 4 is 16. So you get the idea that this sum right here is simply n squared. So if I want to come up with a pattern, s sub n equals n squared. So what I've just done is I've shown it works for 1, 2, 3, 4, 9, 15. Actually, I didn't show this, I just assumed it. What we need to do is we need to prove it. So how would you prove that? Obviously, you're not going to show all infinite number of cases. So that's how an induction proof works. Don't worry about writing this out if you're taking your notes at home. I just want to go through these steps, and we'll do some of the writing when we get into the examples. It'll make a little bit more sense. So basically, a mathematical induction proof is 3 steps. Show, assume, prove. So you can remember that acronym, SAP. What we do first is we show it works for n equals 1. That's the first term. So basically, I did that right here. All right, when n equals 1, I get 1 equals 1. Then we assume it works for n equals k. And this is the part that's usually a little bit confusing for students, not the actual step, because you just plug a k in for the n, but why do we do it? Because we assume that k is any term in the sequence. So it could be the 10th, it could be the millionth, it could be the billionth, it doesn't matter. We assume it works for that place. Then, what we call the end of the bridge, we prove it works for k plus 1. Because if we assume it works for k and we prove it works for k plus 1, k can be any number in that sequence, so that's sort of how we prove it works in all infinite number of cases. What we do during the proof is mostly algebra, manipulation of expressions, factoring, multiplying, things of that nature. This is pretty important though. In step 3, we always use the assumption statement as a substitution. So again, this doesn't really make a whole lot of sense just writing out the steps and looking at these phrases here. So let's take a look at an example. In this example, I need to prove that the summation, remember that's a summation, as I goes from 1 to n of 2i minus 1 is equal to n squared. First thing I want you to do whenever you have a proof by induction and you're given a summation is I want you to expand this. So what we do to expand, remember, is we plug in a 1 right here. So what does that give me? 2 times 1 minus 1? Well, that's just a 1. Since this is a summation, I need to add all my terms. And now let's plug in a 2 here. It goes 1, then a 2. So 2 times 2 is 4, minus 1, that's 3. Then let's plug in a 3 here. 2 times 3 is 6, minus 1, and that's 5. Well, this is what we just talked about on the other page, right? This is going to be the sum of the odd integers. So we usually do the first 3, and then we do the last. So the last is what I get when I plug an n in here. That's 2n minus 1. That has to equal n squared. So this here is the expanded notation of this summation. Basically what I'm saying here is if I add a series of odd numbers, it equals to the number of numbers squared. All right, so let's start the proof. Show it works for n equals 1. Well, when n equals 1, I just have to plug a 1 in here and plug a 1 in here. We have to show that. I know it seems a little bit silly, but it's part of a proof. So this will be 2 times 1 minus 1 equals 1 squared. Well, 2 minus 1 equals 1, 1 equals 1. Yeah, that works. Now, I assume it works for n equals k. Basically, we just take this expanded notation and we replace the n's with k's. And again, I know it seems kind of silly, like why don't we just use n's? Because k represents any spot in that sequence. Like I said, it could be the 10th, the millionth, billionth. So I rewrite that expanded notation. 1 plus 3 plus 5 plus dot, 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 plus 2k minus 1 equals k squared. So now this next step is the crucial step. What this is saying now is prove it works for n equals k plus 1. Well, if you think about how a series works, 1 plus 3 plus 5 plus 7 plus 9 dot, dot, dot. Well, in order to get the next term, you need to include all of the terms prior to it. So if I want to list out this sum, I have to include these. So this right here is kind of like the k plus 1 term. So what that means is I need to include all of this in this step down here. And that's what it said by use the assumption step as substitution. So what I'm going to do first, I'm going to use a highlighter here, is I'm going to use this to start the next step. 1 plus 3 plus 5 plus dot, 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 plus 2k minus 1 plus. So what that is this series here, but then I need to go one more term. So I have to take this rule, and instead of the k, I have to put in a k plus 1. Don't forget to use your parentheses. So what comes next is 2 parentheses k plus 1 minus 1. It's this pattern right here, but instead of this k, you do a k plus 1. Now on this side, you're going to replace the k with a k plus 1. So that's equals k plus 1 squared. All right, so now notice what I've highlighted. These two series are exactly the same. Those are equal. Well, since this is equal to k squared, I can take k squared and replace all of this stuff. And that's what I'm going to do now. I'm going to take k squared and replace all of that. Then I rewrite this statement here. Okay, so that's going to be k squared plus 2 times k plus 1 minus 1 equals k plus 1 squared. Now you're past the hardest part. That's the hurdle. The rest is pretty simple algebra. What you need to do now is you need to make the left side of this equation equal to the right side. So you're just going to do some distributing, foiling, whatever. Sometimes you might have to factor, but basically you just need to get those two sides to be the same. So this gives me k squared plus, let's distribute here, 2k plus 2 minus 1 equals, that's going to be k plus 1 times k plus 1. Combine like terms on the left, I get k squared plus 2k plus 1. And over here, if I FOIL this out, it's k times k, which is k squared, plus k, which is plus 2k, plus 1, and I've got the left side equal to the right side. I've just proven this identity. Okay, let's try this again. After a few examples, I think this will start making more sense. The only part that's really going to change is this algebra right here. All right, and occasionally, depending on the expression, that can get a little bit more tricky as we progress. Okay, number 2. I want to prove this particular summation. Summation as I goes from 1 to n of 2i equals n times n plus 1. So remember, the first thing we're going to do is let's expand that. We do that by plugging in a 1 here, and 2 times 1 is 2, plus, then I plug in a 2 here. 2 times 2 is 4, then plug in a 3, that's a 6, first 3, and now plug in your n. Plug in the n right here, so that's going to be 2n. That equals n times n plus 1. So now if you notice here, they don't list out the steps. Show, assume, prove. You just need to know those steps. On the exam, work packet, work session, you're going to have to write this stuff out. So it's just part of the proof. Show, assume, prove. Show this works for n equals 1. Well, what you're going to do then is you're just going to plug a 1 in here and a 1 here. Okay, so that gives me 2 times 1 equals 1 times 1 plus 1. That's 2 equals 1 times 2, or 2 equals 2. Yep, you've just shown it works for n equals 1. Next, assume n equals k. That's where you use your expanded notation. And generally, when we get down to here, I don't bother writing that third number out, but make sure you include the first two and the last. You can use a k instead of an n. So this is 2 plus 4 plus dot 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 plus 2k equals k times k plus 1. Next, we prove this works for n equals k plus 1. Now remember, you must include all of this in the next step. So I'll start by taking 2 plus 4 plus dot 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 plus 2k plus, what would the next term be? It's going to be 2 times k plus 1. That's going to go right here. 2 times k plus 1 equals. Now over on the other side, you have to replace this with a k plus 1, and you replace that with a k plus 1. Use your parentheses. This becomes k plus 1 times k plus 1 plus 1. Now again, if you notice, these two pieces of the series are equal. Since that's all equal to k times k plus 1, I'm going to substitute in here. This becomes k times k plus 1. I am replacing this with that. Now you just bring down the rest and work it out. Okay, so now I'll do a little algebra here. My general rule is you can do one step in your head per line, if you will. So I'm going to do some mental math here and just distribute that. I'll do some mental math here and combine those. That's pretty obvious. So this will be 2k plus 2. This is going to be k plus 1 times k plus 2. Now I just want to clean up this side. I can FOIL that in my head, so that's going to be pretty straightforward. Distribute here, I get k squared plus k plus 2k plus 2. If I FOIL that out, that gives me k squared plus 3k plus 2. And then lastly, just combine like terms, k squared plus 3k plus 2 here. And that's what I have over on that side. I just proved that identity. Okay, a few more. Next one, I want to prove the summation as I goes from 1 to n of 4i minus 1 equals 2n squared plus n. Again, first thing we're going to do here is just expand. Always do this. Just makes it so much easier to do the rest of the proof. So again, let's take a 1, plug it in here. I'm just going to do this in my head. 4 times 1 is 4, 4 minus 1 is 3. So the first term is 3. Plus, now let's take a 2 and plug it in here. Well, that's going to be 8 minus 1, that's going to be a 7. Take a 3, plug it in there. That's 12 minus 1. That's going to be 11. So you can see the pattern here. Plus, dot, 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 plus, plug in your n. 4n minus 1 equals 2n squared plus n. Now we can start the proof. Show it works for n equals 1. And again, what you do there is you plug in a 1 here, here, and here. Okay, so that's going to be 4 times 1 minus 1 equals 2 times 1 squared plus 1. That's 4 minus 1. That's going to be a 3. This is 2 plus 1. That's going to be a 3. Yes, it works. You plug in a 1 to both sides, and you get an equal numbers. Perfect. Assume it works for n equals k. So this is where you use your expanded notation, and you plug in a k for all your n's. That's going to be 3 plus 7 plus dot, 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 plus 4k minus 1 equals 2k squared plus k. The next is your prove. Prove n equals k plus 1. Again, this is where it's critical. I cannot emphasize this enough. You must include this here. All right, so that's going to be 3 plus 7 plus dot, 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 plus 4k minus 1, plus the k plus 1 term. So this is where the substitution might get a little bit tricky. This is 4k minus 1. Instead of the k, you're going to put in a k plus 1. So that'll look like this. 4 parentheses, k plus 1 minus 1. And then over on the other side, this gets replaced with a k plus 1 in parentheses. Then you're going to square it, and that's going to be a k plus 1. Okay, so that gives me 2 parentheses, k plus 1 squared plus k plus 1. Okay, now the next thing we're going to do, I hope I have enough room here, but we are going to replace this part of the series with that. All right, again, here's why they call it a bridge. Notice these two are the same, and since this is equal to 2k squared plus k, I can swap that out. So basically I take that expression and replace this stuff right here. So that's going to be 2k squared plus k, and then the rest of it I'll distribute here, plus 4k plus 4 minus 1 equals. Now, you're going to do several of these. So it's probably a good idea that you can do k plus 1 squared in your head without writing it out. K plus 1 squared is k plus 1 times k plus 1, which equals k squared plus 2k plus 1. All right, remember, you're doing FOIL. So I usually go right from here to that step. And if you kind of know that in your head, it's going to save you a little bit of writing. So I'll keep the 2 out front, and then k plus 1 squared is going to be k squared plus 2k plus 1 plus k plus 1. So now I just need to combine like terms, put stuff together, distribute, whatever it takes to make this side and that side equal. Okay, it's pretty simple algebra. This here will give me 2k squared plus k plus 4k is plus 5k. 4 minus 1 is a 3. Over on my right side, let's distribute first. 2k squared plus 4k plus 2 plus k plus 1. One more step. 2k squared plus 4k plus k is plus 5k. 2 plus 1 is 3. And check it out. You've got the same thing on both sides. You've just done that proof. One thing I just want to caution you guys against, please don't go from here directly to something like that. All right, you have to show the work. Okay, 2 more. One pretty easy one challenging one. So in example 4, one thing I notice here is that this is already expanded. Great, saves me a lot of work. All right, that's the expanded notation, 4 plus 8 plus 12 plus dot, 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 plus 4n equals 2n squared plus 2n. So let's start with our show. It works for n equals 1. So there's a couple ways you can do that. One way is to understand n equals 1 just represents the first term. So you do this. Oh, there's my first term, 4. I just put a 4 here. Or just plug a 1 in for the n in your rule. That's generally what I do, but there's just a couple ways you can do that. And then over on the other side, obviously plug in your 1 in both spots. So this is 4 equals 2 plus 2, 4 equals 4, good. Next, we're going to assume it works for n equals k. So I've got 4 plus 8 plus dot, 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 plus 4k equals 2k squared plus 2k. And before I even get to the next step, I'm just going to remind myself that I need to include this in my next step. Well, next we're going to prove it works for n equals k plus 1. And yes, you do have to write these statements out. It's part of the proof. Okay, so it's going to be 4 plus 8 plus dot, 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 plus 4k plus my next term, which is going to be this, but I replaced the k with a k plus 1. So it's 4 parentheses k plus 1. And then over on the right side, I have to replace that with a k plus 1 in parentheses. So I'm going to square it, and then this will have parentheses as well. So that'll be 2 times k plus 1 squared plus 2 times k plus 1. Now, I take this expression here, 2k squared plus 2k, and I replace all this highlighted stuff. 2k squared plus 2k, right? Again, the concept is, well, this equals that, and since these two are equal, I'm just going to replace this stuff with 2k squared plus 2k. All right, the rest should be pretty straightforward. I'll distribute here. I get 4k plus 4. K plus 1 squared, we see that again. That's going to be k squared plus 2k plus 1. And I'll distribute over here 2k plus 2. So that's the most I want to see in one step. I don't want you to do anything else in your head, even if you're able to, because remember, it is a proof. You have to show a sequence. On the left side, let's combine some like terms. 2k squared plus 6k plus 4. Okay, so now over here, let's distribute the 2. 2k squared plus 4k plus 2 plus 2k plus 2. And then lastly, I just need to combine like terms. 2k squared plus 6k plus 4. And that's exactly what I have over there. So I've just proven that identity. All right, now the last one, this one's going to be fun. All right, as you can tell already, we have a fraction. Students usually freak out when we see fractions, but this one's not too bad. Get to use some high-level algebra. First, let's expand. Okay, what would I get if I plug a 1 in here? Well, that's pretty easy. 1 squared. That's just 1. Then plug in a 2. 2 squared. Well, that's 4. 3 squared. That's 9. Plus dot, dot, dot. Plus n squared equals n times n plus 1 times 2n plus 1 all over 6. Yowza. Okay, first, show it works for n equals 1. Okay, well, on the left side, I just get 1 squared. On the right side, I get 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. Okay, well, that's just 1 on the left. But let's see, that's 1 times 2 times 2 times 1 is 2 plus 1, that's 3 all over 6. That's 6 over 6, 1 equals 1. Yeah, that works. Okay, a little bit more effort than what we've done in the past for step 1, but that does work. Next, assume it works for n equals k. So I take my expanded notation right here, and I just replace all my n's with k's. Okay, so I got to scroll a little bit. So that's going to be 1 plus 4 plus dot, 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 plus k squared equals k times k plus 1 times 2k plus 1 all over 6. So remember, here, I have to copy this part of the series down here and then add another term to it. That's the prove step. Prove this works for n equals k plus 1. So I have 1 plus 4 plus dot, 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 plus k squared plus my next term, which would be k plus 1 squared. The rule is squaring. So if I have to put in a k plus 1, I have to square that. Now here's where it gets a little challenging. Over here, I have to put in a k plus 1. There, there, and there. Please don't try and do too much in your head. I don't do anything in my head. I just show the straight substitution, and I have to include parentheses. This gets replaced with a k plus 1. So I need to use parentheses. K plus 1. This gets replaced with a k plus 1. It's in that parentheses. So that's going to be parentheses k plus 1 plus 1. Right? Where does that come from? I replace that with a k plus 1, and then don't forget you always have that other plus 1 in the parentheses as well. And the next one is a little tricky. It's going to be 2 parentheses k plus 1 plus 1. All of that over 6. All right, well, here's the challenging part. I need to take this expression here and plug that into this piece of the series. Again, the concept is, well, these two are equal. Okay, great. And this is equal to that. So I can put that right in here and then work out the rest. So that's going to be k times k plus 1 times 2k plus 1 all over 6. Then the rest of it plus k plus 1 squared equals k plus 1 times, now you can simplify this, that's going to be k plus 2. All right, so I'll do that. And we can simplify that. I'm going to distribute and then add a 1. So that'll be 2k plus 2 plus 1, or 2k plus 3. All of that over 6. Wow. So everybody's favorite, we've got some fractions, right? I need to put these two together because notice I have one fraction here. This is going to involve a little bit of work. How do we add fractions? We have to get common denominators. Well, my common denominator is going to be a 6. So here's what I'm going to do. If I need a denominator of 6 there, I need to multiply the numerator by 6 as well. All right, so I'm going to have something that looks like this. Now, I just want to work with this for a second. There's two approaches here. One of them is called a brute force. I call it a brute force approach, meaning I would take all of this stuff and multiply it out. I would use FOIL on this, get a trinomial, then I have to multiply that by a binomial, which means distribute to 2k to 3 terms, distribute to 3 to 3 terms, and then combine like terms. That's going to be a little bit much. You can do it that way. Here's what I'm going to do first. Let's combine this stuff. What's that look like? Well, that looks like this. K times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared all over 6. You have to keep writing the fraction. Remember, my goal is to somehow get this to look like that. Well, I've got the 6's taken care of. This is the product of 3 factors. If somehow I can factor this stuff here, well, notice what we have. K plus 1 here, k plus 1 squared here. I can sort of do, not sort of, I can do a GCF. Let's take out a k plus 1. All right, so if I take out a k plus 1, I'm going to be left with this expression without that. So it's k times 2k plus 1. Over here, I take out one of these, and it's 6 times k plus 1. So it's plus 6 times k plus 1. All over 6. Now, I'm constantly comparing what I have here to what's up here. Notice what we now have. I've got this k plus 1 on the outside, and I've got a k plus 1 on the outside here. So basically, I've got two approaches. I can work with this expression and then maybe just multiply these two together and get what I would get if I multiply that out. Or you can multiply this stuff out and then factor it to get that. So I'm going to do a combination. I'm going to take this piece here and let's just multiply out these pieces. All right, because I think I can do that in my head. I've got k plus 1, that doesn't change. So here I'm going to have k times 2k, that's 2k squared. This gives me 3k, that gives me 4k, so together that gives me 7k. And 2 times 3 is 6. So now it's not as bad as you might think because all we need to do is to get this stuff right here to be 2k squared plus 7k plus 6, and I've got everything else in place already. So I'm just going to distribute, but first, yes, you have to write all this stuff out every time. So let's distribute here. That gives me 2k squared plus k plus 6k plus 6. And lastly, combine like terms. So I get k plus 1 times 2k squared plus 7k plus 6 all over 6. And now you can compare. This expression and that expression are equal, so you've proven that identity. All right, so that was a lot of fun. Some good algebra review in there. That concludes day 6. Thanks for watching. Thanks for hanging in there. I know this is brand new and a little bit challenging, but we're going to do some more of these in lesson 7. And then you should have a pretty good grasp on this. As usual, guys, if you have any questions, don't hesitate to reach out. We'll see you in class soon.